Hello 8th graders, this is Mr. Warrington. Welcome to the Edpuzzle lesson on problems associated with absolute dating methods. In this lesson, what we're going to do is take a look at those dating methods that we talked about earlier in the week. We talked about erosion being used to date rocks. We used varves to date rocks, and then we also talked about the use of radiometric dating to determine how old a given rock is. And what we're going to do today then is just talk about the problems with each of those methods of trying to determine the absolute age of things. And again, we're working with historical science here, so it's not an exact science, and so we have to examine these things and then kind of get an idea of how accurate or inaccurate those different methods may or may not be. So make sure you have your notes packet. Make sure you have something to write with. Don't forget, you can pause whenever you need to. You can replay if it's in between questions. And hope that you learned something from all this. So let's start out with the first one that we talked about, and that was erosion. And remember, erosion is just the wearing away of rock, usually by water, but it can also be by wind, chemical weathering, other things like that. The idea behind it was if we know the rate at which erosion has taken place, and we know how much erosion has occurred, then we can figure out how old the rock is. And the problems with that are basically that it assumes that the principle of uniformity is correct. And as we mentioned in class, there's some questions about whether or not that principle is correct. And one of the reasons for that is it does not account for catastrophic events, such as Mount St. Helens, for example, or even a worldwide flood. And so the idea is that just because erosion is taking place at a certain rate right now doesn't mean that it's always gone at that same rate. It may have gone faster in the past. It may have gone slower in the past. We can look for evidence that might indicate whether it's happened more quickly or slowly in the past. But still, in the end, there are some problems with it. Okay, the second one we want to look at is varves. And if you remember, we said that varves are layers of sediments that are laid down by glacial lakes, and they are laid down at the rate of 1 per year. And we also mentioned that Lake Van in Turkey has basically 500,000 layers or varves in it. Now, what I want you to do is take a look at this picture right here. And this is not varves, but it is layers of rock. And you can see these layers. And when I say layers of rock, probably more likely layers of sediments. It's probably not really what they call consolidated. It's not really hard rock. It's more loose sediments. You can kind of get an idea of that by looking at some of the different parts here, how it's not necessarily real strong. We have a person here as kind of a guide to give us a perspective of how large this is. We can see the top up here. So what I want you to do is to type out how long you think it took for all these layers of rock to form, from the bottom here, where this woman is standing, all the way up to the very top there. Okay, so go ahead and type your answer in, and then we will reveal how old these rock layers are. All right, you've had a chance to do that. Let's take a look at these. All right, the bottom layer was formed in 6 hours, believe it or not, from here to here. Only 6 hours. And that was on, what would that be, May 18th of 1980. The middle layer, all this was formed in basically 24 hours, June 12th if I'm getting my months right here, of 1980. And then the top layer up here took about a month to form, and that was in March of 1982. Now, one thing I have to tell you here is that these are not varves. I don't want you to think that I'm telling you that these are varves when they are not. But they are layers of sediments that were laid down very, very rapidly. And if you haven't figured it out by now, this is near Mount St. Helens when it erupted back in 1980, and then when it erupted again in 1982. But these are layers of sediments that were laid down very, very quickly, even though you can see individual layers in it. And I've been told that if you get up very close to these, you'll actually see things that look very much like varves, very, very thin layers. And so these thin layers were laid down very, very rapidly. So when you have a catastrophic event, things can happen much more quickly than they normally can. So, but let's think about this in terms of Lake Van, as we talked about earlier, and actually varves. And one thing, as people have studied the sediments at Lake Van a little bit more, they've discovered that they're not really varves. There's something that would be better described as rhythmites. And rhythmites are layers of sediments, but they're not laid down at the rate of one per year. They actually can, you can have several rhythmites in 1 year, and you can even have several rhythmites form in 1 year, or I'm sorry, in 1 day. And so those layers at Lake Van do not prove that the lake is 500,000 years old. It just proves that you have a bunch of rhythmites that have been laid down there, and we really don't know how long it took for those to form. So if someone tries to tell you that Lake Van is a good example of the Earth being really old, actually it's not. At one time it was thought that way, when it was thought that those were actually varves, but they're not. They've been observed to form very, very rapidly there. Okay? Now, the one that we're going to talk about the most is the problems with radioisotopic dating. And this is the most commonly used method of trying to date igneous rocks. Now, radioisotope dating does not work on sedimentary rocks, doesn't work on metamorphic rocks, but it does work on igneous rocks. And the idea behind it is that when an igneous rock cools and forms rock, or when maybe I should say magma or lava cools to form igneous rock, that starts the clock. That is the time of the formation, and that is when the radio isotope decay begins. So the three assumptions that we talked about in class, as we related it to me putting pennies in the can, the first one we said was no daughter material was present when the rock formed. That's the first assumption. The second assumption was that the decay rate is constant, and that there's no contamination of the daughter material. And as we said in class, if any single one of these assumptions is incorrect, then it is next to impossible to date rocks using radioisotope dating. The problem is that we have seen evidence that all three of these assumptions may be incorrect. I'm not saying it's definite that they're incorrect, but there's definitely some evidence that suggests that all three of these are incorrect. And like I said, if just one is incorrect, then we cannot, radioisotope dating just doesn't work. So let's look at some examples here of these different of cases where each of these assumptions has been brought into question. The first one is the assumption that no daughter material was present when the rock formed. So when a scientist looks at an igneous rock and looks at like maybe the amount of uranium and the amount of lead in it, they don't know whether there was any daughter material there to start with, and if there was, how much was there. So they make the assumption that there was no daughter material when the rock formed. Now that might be a good assumption, but there's a lot of reason to think that that probably is not a good assumption to make. So, for example, a rock formed in 1980 at Mount St. Helens tested to be 350,000 years old. And we'll take a look at some other things here from Mount St. Helens. And actually, in 1980, after the eruption in the crater at Mount St. Helens, the crater that was formed by the explosion, a volcanic dome started to form. So that volcanic dome didn't start growing until after the eruption. The scientists went there, collected some rock directly from the volcanic dome down in the crater, took it to a lab to be tested. And the first thing they were asked when they brought that in was, where did you get the rock from? And these scientists said, we're not going to tell you where we got it from. If this process works, you should be able to tell us how old it is. And so they took it, tested it, and they came out and said that it's 350,000 years old. When it is obvious at that point in time, and I can't remember what year they did this in, but at that point it was only between 20 and 30 years old, but yet still it tested out to be a third of a million years old. Okay. Another rock formed by lava flows at a mountain in New Zealand that I cannot pronounce. The lava flow occurred in 1954. We know that it occurred in 1954 because we have records of that lava flow and the places that it went. So these scientists went, got some rock from that volcanic flow, that lava flow, and took it in, and it tested out to be 3.5 million years old, even though it was probably only 50 or maybe 60 years at the oldest at the time that it was tested. And then another one is rock at the top of the Grand Canyon that was formed recently, was tested to be over 1 billion years old. Now, let me tell you about this rock. On the north side of the Grand Canyon, you have what's called the North Rim area. There's a big plateau there, and on that plateau is a volcano, and it's actually pretty close to the canyon. That volcano erupted at some point in the past. We're not exactly sure when it erupted. Then that rock flowed into the Grand Canyon and flowed over some of the sediments there. The problem is, well, there's a couple of problems. Number one, when it was tested to be over 1 billion years old, that meant that it was much older than the sedimentary rock that it was sitting on top of, which, if you think about it, that's impossible. The other thing is, in that area, in caves, they have cave drawings done by Native Americans showing the volcano erupting. So that volcano is only a few thousand years old at most, but yet the rock in it, the rock that from the lava flow, was tested to be over 1 billion years old. And all of these issues had to do with that relationship between the amount of daughter material and the amount of parent material that was present. And when the labs conducted these, they assumed that there was no daughter material. All right, the second problem, oh, I forgot. Here is a picture of the lava dome inside Mount St. Helens. So all this used to be mountain. The peak went way up here. This is something like a couple thousand feet right here, and the whole thing lost a couple thousand feet off the top. But after the eruption, this dome right here started forming. So this rock all has hardened, been turned from lava and magma into rock at least since 1980, if not more recently than that, because it's continuing to grow all the time. So the very oldest this rock could be would be 80 years old, even though it tested out to be a third of a million years old. All right. Okay, the second assumption is a constant decay rate. And scientists don't know how quickly radioactive atoms decayed in the past, so they assume that they have always decayed at a constant rate. Now, to me, of all these problems, this is the one that I find hardest to challenge for myself, because I can't imagine why they would have decayed at a faster rate in the past. But yet there is evidence that they have decayed at a faster rate in the past than what they do today. So let me give you this example here. In New Mexico, they found some zircon crystals, which are igneous, and those zircon crystals showed two different ages depending on which test was used. So the first way they test them was to measure the amount of uranium compared to the amount of daughter material, and that gave an age of 1.5 billion years. But if you remember, and this is why it was so important to talk about alpha decay, when alpha decay takes place, helium is formed. And so if we take a look at these zircons and then estimate how much helium has been lost from them, they haven't lost very much helium. And so compared to the amount that was formed inside them, and so the amount of helium that has been lost gave them an age of only about 6,000 years. So you have two different methods of trying to date the same rocks, and you come up with vastly different numbers, 1.5 billion years or 6,000 years. Now, to explain this, if radioactive decay happened more quickly in the past, then the rocks would be much less than 1.5 billion years, maybe even as few as just a few thousand years, which is what this right here indicates. So I'm not saying that radioactive decay in the past necessarily did happen, but yet there's some evidence here that it actually did. And so sometimes, even though we can't explain it, we have to kind of look at the evidence and follow it where it leads us. So there's quite a few scientists, especially creation scientists, who believe that radioactive decay happened much more quickly in the past for some reason. But again, I can't explain myself why that would be. I would have to have a degree in nuclear physics in order to do that. All right. The third assumption is no contamination. And again, scientists don't know how much contamination has occurred, or even if any has occurred, so they assume that there has been no contamination. But if contamination has occurred, then that would change the age of the rocks. Now, let me tell you what contamination would be, and that is you could have water coming from one area that might have a lot of lead in it and carrying it into the rock that we're testing, and that would impact the results of our test. Or maybe lead got washed out of the rock that we're looking at, and so that would impact the result of it as well. Okay? So in this mountain, on this mountain in New Zealand, with lava that was known to be less than 50 years old, they went and collected rocks from 3 different locations. And in those locations, there was evidence that there had been some contamination. So those rocks were taken in, to a laboratory. The laboratory ran their tests on them, and even though they were less than 50 years old, one of the rocks, or some of the rocks anyway, gave an age of 133 million years. Some rocks that were collected from a little bit different area gave an age of 197 million years, and others that were gathered from yet another area gave an age of almost 4 billion years. But remember, these were all from the same lava flow that was less than 50 years old. Now, in all of this, what I want you to keep in mind is that when it comes to radioisotope dating, there are a lot of questions as to how accurate it is. And radioisotope dating is kind of like the principle of uniformitarianism. It's kind of one of the sacred cows of geology, because if it doesn't work, then all the science that's been done and all the exploration and science that scientists would like to do really has no basis. And so then all that work would have been done for nothing. All of our evidence that the Earth is really, really old comes to nothing. And so there's really a big ruckus that comes up when creation scientists try to point these things out. And again, it really comes back to presuppositions. If your presupposition is that the Earth is really, really old, then you'd expect really, really old ages. If you think that the Earth is really, really young, then you would expect there to be some problems with the methods that tell us that the Earth is really, really old. But yet the evidence is there that there is a problem, or there's many problems with radioisotope dating. All right, well, that wraps up this lesson. I hope you have a good, restful weekend, and we will see you on Tuesday. All secure in Sector 7. Bye-bye.